Okay, so number 55 here states that a 200 kilogram weather rocket is loaded with 100 kilograms of fuel and fired straight up. It accelerates upward at 30 meters per second squared for 30 seconds, then runs out of fuel. Ignore any air resistance effects. A, what is the rocket's maximum altitude? And B, how long is the rocket in the air before hitting the ground? Okay, so we're going to start off with what we know. So what we know is that the initial acceleration is 30 meters per second squared, and the change in time initially is going to be 30.0 seconds. So we're going to use this to find the velocity of this balloon just by multiplying these two terms together, and we get 900 meters per second. And then we're also just going to note here that the second acceleration for another part of this question is going to be equal to gravity, which is equal to negative 9.8 meters per second squared. And here are the two formulas or equations we're going to be using for this question. So this question is built into two parts. We have an acceleration stage and a deceleration stage. The acceleration stage when it is accelerating upwards, and the deceleration stage when the rocket runs out of fuel. So this is what the acceleration stage looks like. We're going to be basically finding this distance here until it runs out of fuel in 30 seconds. So we're going to take this equation here and just plug in what we know. So we have the initial position, which is 0, the initial velocity, which is also 0, times 30 seconds, plus 1/2 times 30, which is the 30 meters per second squared, times 30 seconds squared. And so we do all the math here, and we find the position of the rocket at t equals 30 is 13,500 meters. And so the deceleration stage looks like this. We're going to be finding the distance from here to here. And at the top of this curve here, our velocity is equal to 0. So we'll be using that instead of the 900 for this part. So because we don't know what t is here, we're going to use this change in s formula to find our position. So we're just going to plug in the final velocity, again, is going to be equal to 0 here because that's the top of where we're going, minus the initial velocity, which is going to be 900 and squared, over 2 times negative 9.8 because that's the acceleration of gravity. And here we're using the acceleration of gravity because there's no more fuel to propel us. So we get negative 810,000 over negative 19.6, which leaves us, if we use significant digits, 41,326 meters. So the total position change, or the maximum altitude, is going to be equal to those two added together, and we get 54,826 meters. Now for part B, how long is it in the air, we're going to be using the t total is equal to t1 plus t2, and that's basically this entire time. So we know what t1 is. T1 is equal to 30 seconds, like what we found, like what we were given. And so we need to solve for t2. So we're going to use this equation again to solve for t, because we know everything else except for t now. So we're going to have the initial position, which is the end of the acceleration stage for t2, plus the initial velocity, which is 900, plus 1/2 times negative 9.8, which is the acceleration at this part here, times t squared. And this is going to look a lot like a function. So we get down to here, and I wanted to multiply by -1 because I really don't like this negative here. So we end up with this. And to solve for t, we're going to use the quadratic formula, which, if you recall, looks like this. And so we plug in all the terms here, 900 being b, 4.9 being a, and c being 13,500. And we're going to disregard the minus here because that's going to leave us a weird negative t. And so we are going to end up with 197 seconds with significant digits taken into account. And so we're just going to add that to our 30 from up here, and we get 227 seconds.